I have been looking at the close range phase noise and amplitude noise of this oscillator, the sideband noise, in previous videos. Now I will look at greater frequency separations from the carrier, and to do that I have to change my system at several points. This is the signal analyzer window of Linrad. It has an artifact, if you will, in that starting already at about 1/3 of the highest frequency, the sensitivity starts to drop. This is the signal while measuring this oscillator, and you can see in previous videos a lot of details around this, but not this slope. It has been visible in some cases, but I have been doing measurements in the flat range near the carrier. This is 2 kHz, 4 kHz. Now I want to go all the way up to 25 kHz. So I will have first to remove this artifact. I have applied the appropriate correction for the phase noise, and now things look much better. There are 4 curves, the 2 power spectra, the imaginary part, which is the red dots, which may be a little bit hard to see, but better when I move the camera, and then the yellow or blue curve, which is the real part of the correlation. That's what I'm really interested in. I have not yet changed the amplitude spectra. They look like that. So this is the difference when looking at the signal from my oscillator through my 2-channel receiver. But I can also apply the internal generator of Linrad by pressing F11. This gives a perfect signal, and it is very low. So I add noise by pressing F7 multiple times, like this. So I add noise, and you can see the noise floor is increasing steadily. So let's make 13.5 bit of noise, and I clear the correlation spectrum. And here we can see what is the accuracy of the new curve, because at some point here it starts to fall off. Now I'm looking at the power spectra of the noise using the internal generator, and I have 2000 averages, so the statistics makes a very smooth curve, and I want to have an error of less than 0.25 dB. That's about here, because half a dB per division. And this is at 18 kilohertz, and the maximum frequency is 24 kilohertz. So I limit the spectrum here. Here is the phase noise plot again. There is something wrong with it. You can see it goes up here towards 18 kilohertz, but there is no corresponding a little bit brighter part in the waterfall here. As you can see at the center, it drops here as it does here. So what is this? Well, it is here. It is now number 1, which means do the baseband filtering in the frequency domain using Fourier transforms. This is fastest at large sizes of the baseband, but when I go for 2, do it in the time domain, Then I have implemented double precision routines for this signal analyzer graph. And then I start again. And you can see now it is flat. And I guess there will be fewer negative values here as they were before, but I'm not sure, I didn't do this before. Anyway, the indicated sideband noise level here is minus 180, or better than that, and the level for the radio itself is minus 162.5 or something. So a larger correlation advantage than from here to here may be unreliable. So I have to look into that separately. In the first place, I would like to look at it with a higher resolution, but the speed of the time domain filtering is very slow when going for large sizes of the baseband transform or the baseband filter. So I will have to rewrite the frequency domain filtering in double precision. The problem is better visible with the internal signal generator. So I press F7 once, and that is the noise is now at 5.5 bit. And then I go for the baseband filtering in the frequency domain. And clear. And I have to move the scale from 200 to, let's say, 160. So this is what I have doing the processing in the frequency domain using single precision. And then I click here again. And this is the processing in the time domain with double precision. And it's below 210 for the correlation spectrum, while here it is about 40 dB worse at the high end, and 10 dB with spurs up to 20 dB or so, 30. So precision has a role, and it increases with the transform size. I am now doing the baseband processing in the frequency domain, means there is 1 here, and the routines are rewritten for double precision. So I have full accuracy now. The sampling rate is 96 kilohertz. I changed from 48 from the sound card. And the sampling rate in the baseband is also 96 kilohertz now, which means that the phase noise goes from DC up to 36 kilohertz, and then there is the fall off that I have eliminated. This curve is taken with a fairly large size of the FFT. You can see N equals 15, that's 32,000 points, and the X gain is 0.1. It means each pixel is the average of 10 data points. So what I can see here after 2 hours is that the imaginary part at higher frequencies is larger than the real part, and accidentally the real part happens to be positive, but the fact that the imaginary part is bigger shows that there is some crosstalk between the channels, and as it happens, it comes in the imaginary part at higher frequencies. It seems to come with a negative sign in the real part in this range, around 15 kilohertz, and only up to a few kilohertz it seems I can trust this system. So there is no need to look at the higher frequencies, so I changed the X gain here to, let's say, 0.5. This means 2 data points for each pixel. And here we can see the part of the spectrum where the method really works. It's up to about 500 hertz here. We have a smooth yellow curve. And here maybe down to about minus 180 dBc per hertz. It is reasonable to trust this method. And I now swap from phase noise to amplitude noise. And it is similar. After 2 hours I can trust the result up to about minus 80. But when I looked here, 0.1 for the full range, it is the same. There is the imaginary part that grows. So it's hard to really draw any conclusions from this study. And waiting much longer will make this curve more nice looking. The imaginary part will become more like a line and not scattered points anymore. But it doesn't tell me how to interpret the results. The crosstalk could be in the sound card or somewhere else in the setup. And finding out will be very difficult. A couple of hours later, statistics is a little better. Not much, but a little. Here is the imaginary part, and it comes at minus 185. And the real part is about 3 or 4 dB lower. So minus 185 is the total crosstalk. And similarly, at about 15 kilohertz, the real part is minus 185, 186 really, and the imaginary part is 3 or 4 dB lower. So the crosstalk is fairly similar, but the phase shifts by 90 degrees from 30 kilohertz to 15 kilohertz. And then at lower frequencies I cannot say what is going on, because real part and imaginary part are similar, but probably what I see here is also crosstalk. I have connected this signal generator 30 kilohertz above 10 megahertz, and I have set the level for the amplitude margin on the AD converter here to be 1 dB. And I can see in the other channel the margin is 59 dB. So it means there is some signal there. I have calibrated the S meter so it shows 0 for channel 2 where the signal is injected, and I can see that the undesired coupling to channel 1 is minus 67 dB. I have disconnected the 2 cables for the channel 1 sound card, first one of them and then the second also. And now the isolation is 98 dB. So the sound card sets a limit at minus 98. That is 30 decibels better than I had with the whole system. This is the quad audio amplifier in front of the sound card. I have placed dummy loads on channel 1 and look at the crosstalk. And now it's minus 95. So it is about 3 dB worse. Means there is some crosstalk here. I could make that smaller, but that's not a main issue. I have now collected correlation averages for 40 hours. Since the higher offset range was not useful, I have reduced the baseband sampling rate by a factor of 16. And I'm still running at 96 kHz for the sound card. I have compressed the spectrum. That is by setting the X scale to 0.02. It means that each pixel here is the average of 50 data points in the FFT. So the number of averages is 66,000 times 50 for each data point. And I will save this, and as well as expanded images of the same run to evaluate from paper, and also to have saved the data for possible future use. Here each pixel is the average of 20 data points, and it is very clear from here that there is a negative signal on the real part, and it seems to be frequency independent. And since it goes down here, means there is a positive contribution from my test object, my oscillator. And at this point, 1.05 kilohertz approximately, I have alternating between positive and negative, which means that the positive part and the negative part that contribute, they are equal. So if this thing is horizontal, and it is at minus 183, I should conclude that my oscillator is also at minus 183. Here each pixel is the average of 5 FFT points. And we could have seen from the previous images, but also here, that I can probably get a reliable reading at 400 Hz. Here at 500, the imaginary part is equal in strength as the real part, and I think the data here is too uncertain. Here is 1 point for each pixel. At close range, the result is completely wrong, because, as I found now when I saw this, that the low-pass filter for the phase lock between the two oscillators is set at the shortest time constant. So one oscillator is modulated by the other up to about 10 Hz. So I cannot use the data points here. And the phase angle for that modulation is a little bit like maybe 90 degrees at this range, or up here, and here it's 180 degrees. I don't know exactly, but that was a mistake. But I can use the higher points. Here is the amplitude noise. I don't know how to interpret this. Probably values above, let's say, 200 hertz offset are not accurate. I don't know. Here is amplitude noise with 10 data points for each pixel, and maybe 250 Hertz here is reasonably accurate, minus 179 dB. But otherwise, I think this system is not good enough. And it's obvious here that below 50 Hertz this curve is not correct anymore, because of my mistake on the time constant. I have set the time constant properly, the longest I have, and rapidly I can see the amplitude noise at close range. At 10 Hertz it's about minus 151, and I have waited now 1.5 minutes only. The phase noise is different, because the phase noise of my local oscillators for the receiver is pretty high. So I have to wait to see the test object here. This is 29.5 hours, and the scale is 2 pixels per point in the X dimension. And it is 5 Hertz here, so about here is 5 Hertz. So I will evaluate this and save on paper. I have to change scales, both X and Y. The baseband bandwidth, the filter here, by which I extract the phase of the carrier, it's about 2 Hertz, maybe 2.5, which means that the highest modulation frequency that comes through this filter is half of that. But sometimes the carrier is a little bit on the side, and then I get the modulation from one sideband only, so frequencies up to about 3 Hertz are questionable. That is here. But I think maybe I can trust this thing from 3 or 4 Hertz and upwards. Although I have to take care of spurs in a reasonable fashion. Now the curve looks perfectly normal all the way up to 2.2 kilohertz, which is the maximum with the baseband speed that I have been using now. So I don't know what happened, why I had a negative signal in this upper frequency range before. I don't know if I can trust that the indication here, minus 177 or up to minus 179 dBc per Hertz, if that is really a property of my oscillator, or if it is some artifact of the test system. Note that the imaginary part down here is horizontal and well below the real part of the correlation average. And here is the amplitude noise. It's also well above the imaginary part here. So I can look at the total power, means average of real part and imaginary part. The sum of the squares of the real and imaginary parts for AM and for FM, and that is equal all the way up to about, or down to about 400 Hertz or 500 Hertz. Here is the sideband noise I can read with the fast PLL filter and the slow PLL filter. Below 10 Hertz I get negative values with the fast filter, and that's natural and no problem. And up to 25-30 Hertz, it's a bit uncertain perhaps. Anyway, going at higher frequencies I see a difference, and these are the values. Above 1.5 kilohertz the real part is negative again with the fast filter, and this seems to me to indicate that the stop band attenuation is inadequate for the fast filter. When I plot it, it looks like this. So the green dots on the black curve, that is with the slow filter, and this looks quite normal. But the red curve with the red dots, it has a higher noise level, but towards the ends it has a much lower, because there is the contribution from a negative signal. To investigate the problem, I am injecting a signal here between the Schottky, into the cable between the Schottky mixer and the PLL amp, which contains the filter. So I have injected a audio generator to this point through a 1.2 kilo ohm resistor, and the audio generator is attenuated with stepped attenuators, so I can change the level because I need a very large dynamic range for this. The frequency modulation goes into channel 2 through the varicap that's controlling the frequency of this oscillator, and channel 1 should be unaffected. The frequency is 6 Hz now, and attenuation is 120 decibels on the stepped attenuators. And I see modulation sidebands on channel 2, the red track, but not on channel 1. And when I read the power spectrum of channel 2, the red curve here, I see minus 76. 10 Hz comes here at minus 83 or so. 20 Hz, it comes here at about minus 94. And I will just continue like this. I have a table looking like this. Fast, that is setting number 1 on the switch that controls the filter. You can see about that in a previous video, what is the schematic diagram. Medium is position 4 and slow is position 6. And these columns look similar, but if fast is at 0, position 4 is 30 decibels below, and position 6 is 50 decibels below on all frequency separations, although I cannot see it above 300 Hz. When I inject the signal through a resistor to this point, I get negative feedback because the phase relation, it wants to keep the same phase with relation to the other oscillator. And that limits the level I can put into here, because there is a linearity problem with the Schottky mixers. So another thing I can do is to just disconnect channel 1. So another thing I can do is to disconnect channel 1 and connect the audio signal directly into the PLL amplifier. It is 50 ohm and the amplifier is designed for a 50 ohm source. This is 0.5 Hertz. This is the input to the amplifier, the high impedance oscilloscope in parallel with the input. And I see 1.45 millivolts peak to peak. On the output I then see 45 millivolts peak to peak. 45 over 1.45, that's 31 times for the voltage gain, and that's close to 30 decibels. Now I have set the frequency for half the amplitude on the output, and that is 12 Hz. So I know now at 12 Hz the gain is plus 24. Now I'm running in normal receive mode and I'm looking at channel 2. Just switch the polarization here. Channel 1 is switched off, it's down here. I have set a level from the signal source, this one, that shows the second order sideband here, 30 decibels below the first order sideband, which is a little bit more than 30 dB below the carrier. And then I calibrated the S-meter graph to show plus 24 dB. It says dBm, but I'm reading 24 dB here. Now, that is the gain of the amplifier in this situation. The gain through the PLL amplifier in the fast setting, it looks perfectly okay. It doesn't flatten out about 1 kilohertz. So the explanation cannot be the PLL filter. I have restarted the sound card, but this time at 48 kilohertz sampling rate for the ADC. And it has been running only for 6 minutes so far. But it doesn't look like before with that negative component at higher frequencies. I will have to wait. But it seems there is a problem now and then with the ADC. 7 hours later, this is what I see. There is this negative signal in the real part on frequencies above 1 kilohertz or 1.5 kilohertz or so. Now I just change the time constant. The loop filter is this box here, and here's the switch. And now it is set for the longest time constant. And then I just reset here. Note that the level we see here, negative and minus 186. And I clear. And wait. Already after 1 hour, I can see I still have the same problem. Nothing changed when I changed the loop filter bandwidth. It seems I have found a problem now. Positive values and very small for large frequency separations. What I did was to disconnect this box. It's for a delta 44. It has been sitting in parallel here, parallel with the UADC4 there. And I just disconnected it. I will connect it back now and increase the gain inside the UADC4 as much as possible and reduce the RF signal to the same extent. That should worsen the problem of noise, correlated noise coming from the delta 44, if that really has been the problem. I move the jumpers of the UADC4 from minimum gain, which I have been using, to maximum gain for all 4 channels. And the delta 44 is now in parallel again. And I have added 15 decibels of attenuation on the input. And I have started collecting average correlation spectra again. The noise floor is much higher now. It's here. That's about minus 151. It was at minus 162 before, so the noise level is 10 times higher. And therefore it will take some time until I get this down, until I can see whether there is some noise or not. But it looks maybe so. This is only 2 minutes, and the number of blue points starts to grow here. Now I have been waiting long enough. At 2 kilohertz, here, the negative value for the real part of the correlation spectrum is at minus 171 dBc per hertz. Here is the screen dump from the measurement that I made in the beginning of this video, when I had a negative value at higher frequency offsets. Now the image is negative because I don't want so much black on the paper, so blue is now red. So here are the negative values, and I can read it at minus 183. So that is 12 decibels lower. But the carrier I have injected is now 15 dB stronger. So I should expect a 15 dB difference, but I see a 12 dB. So things seem to be clear now. The delta 44 is emitting noise into the UADC4, and it is probably emitting the same noise into all the channels. So it is correlated, and it is far below the noise floor of the UADC4. It's as much as here. It goes from 162 and down to 183. Now I have collected spectra for 10 hours. And it looks like this. I have changed the scales and so I'm showing averages of many data points. The level here at 4 kilohertz is minus 189, and it's still very noisy. I have to wait more to see what is the result now. When I expand the spectrum, we can see here that the imaginary part and the real part are equal in magnitude. So the noise is lower than this. Here at 100 Hertz I have a reliable reading at minus 166. Minus 166 at 100 Hertz. Here it comes here. And I didn't look for the decimals. So it seems the green dots that I had, they were okay at lower frequencies. The noise from the sound card was below minus 170 or so. At close range, this is a couple of hertz, up to 10 hertz or so. I have these spurs. So I restarted the measurement with a larger bandwidth in the baseband. The reason is that if the bandwidth is too small, all the points belonging to the signal don't have the same amplitude on the filter. And to understand it, imagine the extreme. There is only a single point on the peak of the signal. That means each transform, when back transform, will be just a single sine wave. The next transform will be also a sine wave, but it will have a jump in its phase. And the same phenomenon occurs also here, when there are a couple of points of the signal that are without full level. To eliminate this problem, I just have to make the baseband filter, the narrow filter here, a bit wider, in order to make sure that the entire signal from here to here is within the flat region. Also, when it drifts up to the point where the AFC moves it back to the center. I did that, but the result was not what I expected. I got negative values on the real part, and that was with the wider filter. And then when I wanted to restore what I have seen just recently, it's not possible anymore. Also with a wider filter, also when running with decimation in the time domain, I still get these negative values. They are low at below minus 180 dBc per hertz, but they make it impossible for me to make any reasonable conclusions on what would be the phase noise level above 300 hertz or something like that. I have rebooted the computer as well as the sound card, but I still have this problem with negative real part on the correlation average at something like minus 182 or minus 183 dBc per hertz. And I don't know the reason for this. The signal power is 1 watt, so the thermal noise from the dummy load on the hybrid on the input to the two channels, that has minus 174 dBm per hertz, and 30 decibels above that is the signal. So what I see here cannot be the thermal noise of the dummy load, which is otherwise a problem encountered in correlation averaging measurements. It seems I cannot trust the results I got here. So I need to do some changes to the hardware to be able to look above 1 kilohertz or so. But before doing so, I will check whether this bending here is true or not. To that end, I have set the flat bandwidth of the baseband filter to about 1 hertz. To about 0.5 hertz. And I have set the bin width here of the signal analyzer transform to something like 0.2 hertz. This is 1 hertz per division. And here it is 1 hertz from here to here. And I have to wait, but I put the mouse cross here at the value I currently have, minus 122 at 4 hertz. And it is now only 9 minutes. So it looks like perhaps the result I get now is going to be a little bit lower. Now, after 10 hours, I see here at 20 Hertz, that is minus 146. And I can try 15 Hertz. That's here. That's minus 142 here. And 10 Hertz here. That's 137. And 4 Hertz here. Minus 123. I could wait a little bit more, but I wouldn't get the accurate results because there have been events of interference. These things here. That is far more clear if I look at the amplitude noise. Because here you can see that the amplitude noise is high above the average power of only 30 spectra. So there have been strong events on the amplitude, and presumably they have also degraded the phase noise a little bit. They are about 1 decibel above the values from before. And here it's about 1 decibel below. So I have to do something about that. Assuming the problem is the crystals in the oscillators, I have knocked on the box. And here is the bad interference. This waterfall is much slower, but you can see the first line here is white all the way. And I haven't seen a contribution here yet. I have restarted averaging now, and it will take some time before I have a new curve here. But I will monitor the baseband graph to see whether there are these events still, or whether I have a nice signal all the time. At 4 Hertz here, I was reading 123, that's here. So I will not have to wait a very long time before I can see whether I have a better reading now or not. Here is the AM noise after 5 minutes, and as you can see, it is equal to the AM noise of the average power, or nearly equal to, and not far above as it was before when the interference problems were included. Well, interference, I think that was caused by the crystals, by the epoxy that holds the crystals inside the cans. Events there happen now and then. Now there was an event again. You can see the top line here. It isn't visible here, or it may be already have gone outside the screen. I will run this a little bit slower. Anyway, I go for the amplitude noise here. And it wasn't a strong event, obviously, because the AM noise is, the event is still here, so it is pretty high. I place the mouse on it and wait until I have collected 30 fresh power spectra. I don't know how many already are there, but if I wait from 216 to 240, all the 30 latest should be without the inclusion of this event. And as you can see, the average of 30 transforms, where most of them did not include that interference pulse, that averages was about 6 decibels or 8 decibels above the normal. So I have to do something to eliminate inclusion of these events into the collected average of correlation spectra, because this defect on my system is not what I'm looking for. I'm looking for the noise performance, real noise, not various peculiar events that could be from crystals, but there could be something else also, a poor connection somewhere or some other undesired and really not so interesting phenomenon. 2 hours and still about 123 dBc per hertz at 4 hertz offset. These pulses of narrowband noise occur fairly frequently. It is about 2 hours since start, and I have 6 events. I have disconnected this oscillator and put a dummy load on the output to have it operating normally, while I am now studying instead this Wenzel oscillator. This is in order to see whether the interference pulses I have really originate in the oscillator or whether they are from some other part of my setup. Now, with the Wenzel oscillator, these noise bursts still occur. So they don't come from my oscillator, they are from the setup. Maybe pulses on the DC supply voltages to the amplifiers or the oscillators, or maybe something with the oscillators themselves, or perhaps even with the sound card. Here I have knocked on one of the power supplies and I see a dramatic change on the phase noise. And now I look at the amplitude noise. It looks like this. And it has a very strong phenomenon out here. This is not what I have seen, but it shows that variations on the supply voltage surely affects the performance of my system. While collecting these spectra, I have moved the potentiometers up and down by about 0.5 volts on all the power supplies, and that creates noise on the supply voltages, which has a significant impact on what I see. So maybe the problem is there. The problem did not disappear just because I moved the potentiometers. This is where I started here, and he had one phenomenon after nearly 1 hour. But one is one too much. As it turns out, these narrowband noise pulses, they are caused by the automatic frequency control. If you look at the spectrum here, the peak here is moving a little bit each time. Sometimes not so visible, sometimes more visible. This time not. And the bandwidth is narrow, so each transform collects data. Yeah, I think you could see there it was jumping to the left. This time, no. It is a random walk, I think. And there is also a thermal drift. And I'm waiting. Maybe a little bit later I have more thermal drift, so it will be easier to see. Anyway, there have been many of these glitches, and they should not have been included in the correlation spectrum, because Lindred has a feature that says when I'm doing the frequency control, don't collect the associated data into the correlation average. But there was a programming error, so with these very large transforms it didn't work, so it collected also the transients from the automatic frequency control. And I have fixed that now, and things look better. I think it moved a little bit to the right this time. And this time also. It is clearly moving to the right, and after some time it will reach the point where Lindred decides I have to move it closer to the center, because it is necessary to avoid hitting the edges of the filter, because there are phase discontinuity in the back transform. Anyway, the spectrum is better now, the correlation average. And I have to wait. This is only 2 hours. And, well, focus isn't so good. It is from here. Minus 134, and this is 10 Hertz. This is after 12 hours. There has been an event of some kind. I don't know, because I wasn't here when it happened. But I can see the interference here is much stronger on the mirror, even though the mirror is about 50 decibels below the main signal. and something has been happening, and here it stopped. And this has presumably degraded the phase noise. I expected it to converge to about minus 135. That's where the mouse is now for 10 Hertz. But it seems to be about 1 decibel worse than that. And I guess it's because of this event. I will have a look at the amplitude noise also. It takes some time because I'm running with a very large transform size. And I will change scales a bit. Well, it looks normal at very low frequency offsets. Means it is not above the power spectra. It's very little below, which means that the amplitude noise I see here, it comes from my oscillator and not from the receiver. And the receive oscillators are similar, presumably, in AM noise, or even a bit worse, but they are feeding saturated mixers, and that makes amplitude noise not affect the mixer attenuation. Not much, at least. This, what happened here, has to be related with the ratio between I and Q on one or the other, or maybe both channels. And I have to check for poor connections on all the B and C. Well, here we had something even stronger. And again, it looks like it is a little bit more intense here than it is here. And I could see an increase here. So I will try to, yes, I can see on the amplitude here, it went up, and it was in channel 1. And also in channel 2. I have cleaned all the BNC connectors that could affect the balance between I and Q using isopropylic alcohol, 2-propanol. I fired the local gas station. I have started to collect a new average correlation spectrum, and here is what the main spectrum looks like now. I haven't changed any parameters or signal levels or anything. Nearly 9 hours later, I see the real part of the correlation average. It is at minus 134, and the imaginary part is about 8 decibels below. So maybe it will not go lower than this. 32 hours and 12,000 averages. This is enough at a separation down to about 2 Hertz. And the bandwidth I have now is about 1.5. So this is roughly as low as I can go with the present setup. Looking at the full range up to 1.1 kilohertz with this baseband sampling rate that I'm running at, I can get reliable results up to about here. That is 400 hertz. Now, this is with 0.03 in the gain on the x-axis, means 33 FFT points per pixel. I can do the averaging in the linear power scale far more to get some indication on what happens out here. So I may compress the x-axis a bit. Now, with a much more compressed scale, I can see that at 900 hertz or so, it is 182.5 minus 182.5, and here the last point, I think it was 1.15 or so, it's 183.5. But out here it is fairly uncertain, because the distance from the data points here to the average of the imaginary part is very small. But at 400 hertz here, the result should be pretty reliable when it comes to the statistical errors. And what other systematic errors could be, I don't know. I will save these results and then allow this to run some more time to see if I get a better, statistically better result. Now and then my system crashes, so I would like to have a couple of 100 hours, but that is not so likely that I can have. Temperature variations can cause the oscillators to lose synchronization, and Windows 10 crashes now and then for unknown reasons. When returning, expecting to see the result after 40 hours about, the screen was black. Windows had crashed without any message about the reason. This happens now and then, and I don't know why, but I don't run under Linux because there are problems with the driver for the UADC4. Anyway, here is the result I had after 32 hours. I had saved the files that I showed, that these are the numbers I have. And when I plot them, I get these blue points here. And this is unexpected, because I have seen better results before. The data points fall on a straight line accurately, not exactly but very close to be parallel to this other line here, which is 1 over F3. And it's even hard to see that they are not exactly parallel. As it turns out, I had left this box in line from the oscillator to the two-channel receiver. I made some tests with it to prepare for the wide range measurement that this video was supposed to be about. But now I have been measuring with it, and it adds some noise. I have removed this and started a new measurement, and that was 12 hours ago, so this is 12 hours, and I can see that now the noise at 10 Hertz is at something like minus 135.5. That is here, 135.5. So it's still about 2 decibels above the old value, but it is about 2 decibels below what I had with this phase modulator in line. And I have not waited long enough. Maybe it will go a little bit lower. I will wait and see. Here is the internals of the phase modulator. A ferrite core, some capacitors and some inductors. And the key components are capacitance diodes. Here is a schematic diagram of that phase modulator. It is a hybrid bifilar winding on a toroid, tuned to become a quarter wave on 10 MHz by these two 150 capacitors. So I have the input, 2 here, and the 2 outputs. One input is the RF signal, the other is connected through 4.7 PF and 150 PF to ground, so it's a very small capacitance here, and it can be changed slightly, very slightly, by these capacitor diodes. And it's the same on the other side. So what happens is a very small phase shift, a variation, because this capacitance is so small, and the variations are very small. These capacitance diodes are much smaller than the 150 PF. I don't know exactly what diodes I used, but I think they are 10, 20 PF or something. And there's no bias on them, so the RF voltage here has to be well below 0.6 volts where they start to conduct. And these inductors isolate DC from RF. And here is audio in, and that has to be a fairly small voltage because the peak of the audio and the RF peak, they work together and must not be rectified in the diodes. This video was intended to be about the wide range phase noise, but as you have seen, it has been about all the problems I ran into when doing the very simple thing I wanted to start with, and that was to establish the phase noise at close range. Because when doing the measurements further out here, and even further than that, I wanted to see how it fits to the data at close range, and establishing that should have been a simple thing, but it wasn't. So the wide range will be in the next video, where I will use this phase modulator to establish the level of the frequency modulation sidebands, because to extend the dynamic range I will add a notch filter for the carrier at 700 Hz, and that destroys the calibration since the known attenuation of those carriers may be a little bit unsafe because of frequency stability issues and so, and therefore I need a pure frequency modulated signal to check things. Now I have collected averages for 45 hours, nearly 46, and at 10 Hz I see about minus 135, and let's see what happens at the wide range now without the phase modulator. It looks like minus 182 at 1.1 kilohertz, but averaging is not sufficiently large. It is 18,000 transforms, and the scale is 0.02, which means 50 bins for each pixel. So it means the bandwidth is 50 divided by 3, what that's 16 or something, times, which square root 16, that is 4 times or 6 decibels improvement already. I can compress the x-axis a little bit more, but not much more, because I will not want to have the spurs included, but a factor of 3 or something. Something like this. It gives me 182.5 at 1 kilohertz. And now the imaginary part is significantly lower than the real part, the positive contribution I have there. So this is the result I have, but there could be systematic errors. So I don't have to wait for a better estimate. I can take the statistical errors, and I have to do with another method things to get the noise at above 1 kilohertz. Here is the amplitude noise. It is a little bit lower than the phase noise, all the way up to 1 kilohertz. And here is AM noise and phase noise. At close range, 20 Hz here, they differ significantly, but already at 300 Hz here, the difference is only 2 decibels. This is 60 hours, and I'm looking at the upper part from 800 Hz to 1.1 kilohertz. As a comparison, here is what was saved after 45 hours. And this is clearly less uncertain, but it's still probably plus minus 2 dB or plus minus 1.5. To find out whether this is flat or it has a 1 over f slope, I would need probably something like 200 hours, and not very likely that I will get that before something crashes. Maybe it's better to look at the compressed scale. Here is 60 hours, and here is 45 hours, or 46 actually. So maybe I can see something or read the statistically averaged, well, read what I get with a small statistical error. Remains the systematic errors. I don't know the sign of them and the size. Here is 75 hours, and it compares to the previous result I saved, which is here, 62 hours. And the changes are still pretty large. About 1 dB. The numbers I read now, without that phase modulator, they differ from the previous ones by about 2 dB at very close range and about 1 dB over almost all frequencies except at 1.1 kilohertz, where it deviates the other way. But I don't think this point is valid. It has a too high noise level, and there are other problems also associated with it. That is the influence of the mirror image. You can see the points. The line is accurately 1 over f to the third. And here they start to deviate. That is at 100 Hertz or 150 Hertz. And then this other line is 1 over f to the second. And the point at 1.1 kilohertz is up somewhere here. I didn't plot it because I don't trust it. And I'm very curious as to what happens out here at 5 or 10 kilohertz. Here is phase noise up to 18 kilohertz. I have a notch filter in the audio now at 700 Hertz in all the 4 audio channels. When I compress, it's easier to see. At 18 kilohertz I can read minus 166, and the attenuation of the carrier is about 23 dB, so this means about minus 189. At 1.4 kilohertz there is an artifact here. That is because of the mirror image. The mirror image is 1.4 kilohertz away from the signal at minus 700. The signal is at plus 700 with respect to the center. So this is because of inadequate mirror image suppression. I see the noise on the sides of the mirror, not symmetrically, perfectly, and it seems that noise comes with a negative sign. But I think I can trust the result out here. And also I know that what I see at 1 kilohertz may be a little affected by this. So there are many little things to investigate, and I need to calibrate much better. This will all be in another video. It seems I will find the flicker noise close to where the ruler is now. So the region with 1 over f2 will be very short.